We're going to look at the exponential function and exponential functions. Exponential growth and exponential decay functions is what we're going to be interested in. And we're going to focus our ideas around this function here. For a capacitor, the voltage across a capacitor, or a circuit involving a capacitance. V equals V naught to the power, times e to the power minus t over RC. That's this exponential function. Where V naught is 20 volts, the C is the capacitance, which is 60 picofarads, and R is the resistance, which is 112 megaohms. So here's our example, and there's the circuit. So before we look in detail at this particular circuit in here, this one, this particular function here, just a little bit of introduction to this value, E. We know the natural number, E. And just why this natural number exists, which leads us to these natural logarithms that come up all the time, as you're finding in, particularly in circuit analysis and stuff like that. This number E. If we were to plot the function y equals a to the power minus x, which I've done an autograph here. So if we look down the bottom here, we've got y equals a to the minus x has got into autograph here. A to the power minus x. A is a constant that we can change. At the moment, a is 1. So 1 to the power 2 is 1, 1 to the power 3 is 1. So it doesn't matter what the power of a is in this case, we're going to get a straight line through 1, which you've got. But if I change the value of a, using the constant controller here, then we get this exponential decay curve start to appear. And here it is. And that's the familiar sort of shape you would expect to see on a capacitor. Now, if we change the value of a, the bigger a gets, the steeper this curve, and we can see it. And if I start trying to match this curve to things that occur in nature, then we find that the point at which this curve matches what's going on in the real world is for a particular value of a, and it's the same value every time. And it turns out to be this natural number. And that's because in this sort of exponential function we're interested in one where the rate at which this thing is decaying depends on how much we have. And you remember the differential of the exponential function is one where the differential is actually the same as the function, doesn't change. And that's because the gradient is the value. So at a particular point where the gradient of the curve, at this point, say, the gradient of the curve is given by that value there, that happens when a is at a certain point, and that's the natural number, 2 point something or other. Yeah. So at that point, the curve gives us the gradient that's equal to the value of the function at that point. So that's why this natural number occurs all the time. The rate of change of charge on a capacitor depends how much charge there is left on the capacitor. So it's an exponential function with that natural number as the base. The rate of growth of a population in biology depends on how much of the stuff we've got. The rate of increase of cells on a petri dish depends on how much there is on the petri dish. So an exponential growth with the natural number as the value of the base in that function. So that's what's going on here. This is an exponential function. An exponential function is one where the variable, in this case time, is in the exponent, in the power. So that's why it's called an exponential function. In these particular functions that we're looking at, the base is always the same value, the natural number, for capacitors and things like that. So this is the function that we look at. E is always the same, so it's on the capacitor. calculator, so you can find out values for it. And t is a variable. So if I were to plot voltage against time in a circuit involving a resistance and a capacitor, and there they are, capacitance is 60 picofarad, resistance is 112 megohms, we would get this. And it's plotting the voltage drop across the resistor in the circuit as time goes by. So the voltage across the resistor has a certain value, and we can calculate it using that function. So if I want to know what the value of the voltage is after, say, 15 milliseconds, then I could put the values into the function and work out the voltage. So with this function, and with the added information that the time is 15 milliseconds, calculate for me the value of the voltage after 15 milliseconds, being careful of units. So in my calculator, 20 times e to the power minus 15 times 10 to the minus 3, that's 15 milliseconds, over 112 times 10 to the 6 times 60 times 10 to the minus 12, and we, after 15 milliseconds, we've got 2.1 volts across the resistor. So if I were to put a voltmeter across here, I'd have 2.1 volts, 2.15 volts. What would you expect the voltage across the capacitor to be? 20 minus 2.15, yeah, which is 17.85. Supposedly, okay? What do you think the voltage drop across the capacitor would look like if I had autograph to hand and I plotted the voltage across the capacitor? Sketch it. So at time 0, what's the voltage across the resistor at time 0? 20 volts, and that drops, doesn't it? What's the voltage across the capacitor at time 0? 0. So if I plot a graph of the voltage across the capacitor, it's going to start at 0 and it's going to go like that, isn't it? Okay. What will this value here be? Okay. Exponential growth to a limit, exactly, Tom. So the voltage across the capacitor is an exponential growth to a limit. Now we know what the function is for the voltage across the capacitor. It's the voltage is V naught e to the minus t over RC, isn't it? What will the function across the capacitor look like? Thinking of what we were just talking about. And my phone's buzzing like, my phone's buzzing like mad, and my wife's trying to contact me, so I must just take this phone because she doesn't normally ring me. V, yeah, the voltage across the capacitor. Yeah. So let's call VR the voltage across the resistor, VC the voltage across the capacitor. What will it be? But what V? What value of V? V0, the original voltage minus, right, the voltage across the resistor, which is V0 e to the minus t over RC. Agreed? I can take V0 outside a bracket because that's common to both terms, isn't it? So the voltage across the capacitor is V0 into 1 minus e to the minus t over RC. And that's the classic formula for an exponential growth to a limit. And we can see where it comes from. And it's worth seeing the two together, because if I go back and look at this curve, we can see they're opposites to each other. There's one decays, the other grows to a limit. And so these two formulae, the exponential decay and the exponential growth to a limit, go together, really. So that's an important formula. And that will be the voltage across the capacitor in this particular case. Okay? And there it is. Okay? So V0 equals 20 volts, R equals 112 mega ohms. Again, the capacitance is 60 picofarads. Just to confirm, calculate the voltage after 15 milliseconds by putting the values into that formula, and you should find it comes to the difference between the two, which we worked out already. But just work it out. What's the time for the voltage across the resistor to drop to 15 seconds? So we're back to this original curve, the voltage across the resistor. So we now know the shape of that curve. The voltage across the resistor is going to be an exponential decay. So the voltage is V0, which is the original voltage, e to the minus t over RC. And that formula you should be, very familiar with. What's the time for the voltage across the resistor to drop to 15 milliseconds? Well, how easy is that? Because we've done this sort of rearrangement before. We've got to rearrange this formula now for t. So, rearrange V equals V naught e to the minus t over RC for t. And there we have it. Having rearranged it, something we've done many times. There's the rearrangement. T equals RC log V naught over V. So now you can put in the values and find out for me the time it takes for this capacitor to reach 15 volts. So V naught is 20, V is 15. It's required that the voltage across a capacitor drops by a half in 10 milliseconds. If the capacitance is 2 picofarads, find R. So let's look at this. It's required that the voltage across a capacitor drops by a half in 10 milliseconds. If C equals 2 picofarads, find R. We've got V equals V naught e to the minus t over RC, or we've got that T equals RC log V naught over V. Is that the right way around? Check. V naught over V, yeah. Those are the two formulas we've got so far. We're after R, so we've got to rearrange the formula for R. Which is the easiest formula to rearrange? Right, okay, so we can rearrange the spot and formula for R. It's required that the voltage across the capacitor drops by a half. Do we need to know the original voltage? We just need to know that if the original voltage was, say, 1 Jordan, then it drops to 0.5. So we don't really need to know what V and V0 are. We just need to know that V divided by V0 is a half. And then we can calculate the value for R given that C is 2 picofarads. Would you like to carry on and finish that off? The key point in this is that whatever value V and V0 have isn't important, because if it's dropping by a half, whatever this original voltage is, if I divide it by V0, it's going to be, oh wait a minute, have I got it the wrong way around? Always, yeah. If we're trying to find the value, the time for the voltage to drop to a half, then it's always V0 over V is always going to be 2, always. And if we think about that in another situation, in a radioactivity, for example, we talk about things called half-lives, which is the time for the material to drop to a half, in which case N0, which is the amount of radioactive material we've got, divided by N, which is the amount of material we've got left, is always going to be 2. So we can use the natural logarithm of 2 to help us find out the half-life of material. So with this information, rearrange R equals T over C log 2. So given the value for C and T, we can calculate the value for R in the circuit. So it gives us R equal to around about 7.2 times 10 to the 9 ohms, or 7.2 gigohms. Useful to be able to do that. Okay, if I have an electronic circuit and I've got this particular value of capacitance, 2 picofarads, and I want the voltage to drop at the rate of, drop into a half in 10 milliseconds, that sort of rate, then I could calculate what value of resistance I need in the circuit to give me that. Okay, so I can find any value within the function by rearranging it. Okay. Last thing for today, and then we're going to move on and look a bit more at these exponential functions next week. Homework for you, okay? So let me explain it to you, then you can make a note of it and have a go at it. It's a very easy piece of homework, this, hopefully. I've got a charged capacitor. So let me explain it, and then you can write it so you know what you're doing. I charge up the capacitor. So initially, it's charged, and then I short circuit this thing across a resistor. What I want you to do is to sketch what the curve will look like for the voltage across the capacitor and the voltage across the resistor as it discharges. Okay? Yeah, so all I want from you next week is a sketch of what that will look like as it discharges. What will the voltage across the capacitor look like? What will the voltage across the resistor look like?